Yeah, hi everyone, and thank you so much, Antonia, for the introduction. I also want to speak out a very warm welcome to everybody. And also, since you found your way to this talk, I want to offer my condolences to you, because probably the path to this talk was very painful. But this is a safe space, and hopefully you're going to walk away with some of your PyTorch trauma resolved. So we're going to talk about how to debug PyTorch models today in a structured manner. And as you can see from the title already, honey, I broke the PyTorch model. Breaking a PyTorch model or any machine learning model in general is usually something that happens by accident and is not easily reversible. And the reason usually is that our models consist of many complex components that also work together in a very complex way. So if something is broken, our model is usually still running, and we see that something is wrong, but it's very, very hard to identify what is going wrong. So today we're going to build a little toolbox on what to do when you see something is definitely wrong with my model, but I'm not sure what, and also go through some applications. But before we dive in, I want to give a very quick introduction about myself. My name is Clara Hoffmann. Currently, I'm a PhD candidate at Klein Lab, which is a research lab at the Research Center for Trustworthy Data Science and Security at the University Alliance Ruhr. And in my research, I'm mostly focused on Bayesian uncertainty quantification for deep learning, especially for quantifying predictive uncertainty in computer vision applications. I also worked as a machine learning engineer in production at a startup called Live.io, which is also based here in Berlin, where I was working on computer vision applications with synthetic aperture radar data, which is a very special type of data. You can find the slides to this talk on my GitHub, and if you want to know more about me, you can also check out my website or my Twitter. So let's get right into it. First of all, I want to get everyone on the same page with a quick reminder of what our PyTorch models usually consist of. So for most of you, I think this will be pretty clear already. We usually have our training and validation data packaged in data loaders. We have our model structure set up, which we train with our training loop. We obtain a fixed rate model, and then we usually have some prediction data loaders and obtain new predictions. So what can actually break in the setup? We have three components that are very susceptible to breakage. First of all, the model structure. Usually this is just a stack of layers, and basically what can happen here is I accidentally delete some layers, forget to connect some layers. More obvious mistakes like wrong dimensions are usually already caught by PyTorch. The next component that can break is the training loop. The training loop basically passes the data forward to the model and then propagates the loss. What can go wrong here? For example, wrong loss functions, propagating the loss in the wrong direction. We also have our data loaders. What can happen here? For example, we accidentally only return the same batch in each iteration. But actually, if we look at these components, our model does not seem too complex. We only have three components. So if I'm debugging, basically what should I do? OK, just check every single component, and my model should work, right? The main issue when we're debugging PyTorch models or machine learning models in general is that we usually see that something is broken, but not what is broken. Because when we're training, we're not really seeing what is going on in these components. What we're usually observing is only validation metrics or training metrics like our loss or some accuracy scores. And let's have a little example of why it's really, really hard to identify what is going on in our model only from these loss or metrics. So I have a very small example here, a very simple model structure that you would probably not use in your day-to-day work, just two linear layers and a nonlinear activation function, and I trained a classification model on some classification task with this small model. So on the right-hand side, you can see the loss curves for my model. Yes, I know they have not converged. I just chose some arbitrary number of epochs. You can see the training loss and the validation loss going into the correct direction. And now we have our little breakage toolbox here in the left-hand corner. And we're just going to look at what happens with our loss when we break a couple components of my model. So first of all, let's freeze the weights. Well, this looks as we expected. The model is not learning anything. The red curve, which indicates the losses of my broken model, are just stagnant. Second, let's freeze our bias. okay, actually we have a bug in our model, but our loss curves seem pretty good, actually. So here already we run into some issues. We will probably not be able to see that there's a bug in our model from our loss curves alone. Let's break our data loader to always return the same training example. Okay, here we can already see something is going really, really wrong. The training loss is going steeply downwards and our validation loss upwards, so we're heavily overfitting on the training set here. And now let's break our activation functions. So I'm just getting rid of my ReLU here. And this is quite interesting. So the red loss now looks almost the same like in the scenario when I had been freezing my weights. So this is a very important issue that by just looking at my loss curves, I can see that something is wrong, but not really what is going on. And then my whole trouble basically begins. So what are the main problems when we're debugging models? First of all, bug entanglements. Usually I don't have a single bug, but in several of my components. And when the bug is in something like my data or my data loaders, basically I have no chance to retrieve my bugs without going really heavily into my code. The second factor is that when I'm just going through my code, fixing things, and then running my model again, this is usually not very efficient because, for example, if I have a bug in my data loader, I will never be able to perform any good training because my data is just not having the sufficient information to train a good model. It's also pretty hard to prevent bugs. So, for example, if we had the idea, okay, I'm just going to use some software engineering-based tests to prevent bugs in the first place, this is not really working well because software engineering is a very static framework, whereas machine learning development is very flexible. So usually, if I want to introduce software engineering-based tests, this is more harmful than helpful in machine learning. So what can we do to overcome these issues? I prepared a little debugging cookbook for you, and it basically has 3 components. And our main takeaway here is that we want to isolate each of these components to make sure that we identify any bugs in our error. So the first component is our data. If something is going wrong in our data or our data loaders, we basically have no chance to train a good model. So a very good approach is to create some simple synthetic training data. But I think most of you don't usually do this because creating synthetic training data sounds quite bothersome. The second component is our model, and we're going to look a bit at how to create project-transferable pre-trained tests to make sure that everything in our model is working the way it should be before even starting training. And the last component is the interplay between the data and model. Basically, when we have made sure that our data is working well, our model is working well, but we still see that something is not really right. And here we're going to look at some project-transferable post-train tests to catch any last bugs that we might have in our model. So let's start out with our first component, the data. And I want to start with a bit of a image that is not evoking positive emotions for machine learning engineers. Here we see a domain shift between synthetic data and real data. And usually this is not evoking positive emotions for us because usually we're creating synthetic data to pre-train a model, and then we see our real data is actually completely distant from our synthetic data, and we cannot generalize with our model. Now, I want you to forget any associations you have with this image when you're debugging, because when you're debugging, you actually love this image, because this tells us actually our synthetic data can be as simple as possible if we just want to train a model that is bug-free and cheap to train. We don't really care about realistic-looking data. We just want to reduce our data to the most basic learnable characteristics. And if we have a domain shift occurring between the synthetic data and real data, we actually don't care about this. So one of the main questions I like to ask myself when I'm creating synthetic data only for debugging is, how would a minimalist artist depict my data? And of course, when we're an artist, we kind of have to find our style. We have to kind of find out, okay, like how simple can my data be? How difficult or realistic does my data have to be? And we're going to find this out in a little case study. So we're going to start out with a negative example. I think this will be very standard to all of you. Basically, my goal would be to train a classification model, and I would think about, okay, like how simple do I have to make my data, or how simple can I make my data? So my first idea would just be to generate from 3 Gaussian distributions and assign each distribution a class. So this would look like this. Here I have my data points, and the colors are the labels. And this data looks fine. So what happens if I simulate some breakage in my PyTorch model? So here on the left-hand side, I have a very simple encoder, again with 2 linear layers, and 1 nonlinear activation function. So let's see what happens when I break my activation function. So on the right-hand side, you can see my good model in blue, and the red model is my broken model without activation functions. And this looks quite good on first glance, but actually this is exactly what I don't want. So I'm seeing that with my synthetic data, I cannot even catch a very grave mistake like missing activation functions. So what happened here? Of course, if you look at the data, my data is linearly separable, so it can perfectly be learned by a neural network without any nonlinear activation functions. So this is already the first lesson. Don't make your data too simple. There definitely have to be some nonlinearities in it. And to check that I'm also telling you the truth, let's look at another example with nonlinear data, which are just generated with scikit-learn here. I think these concentric circles are well known to everyone in machine learning. But in general, you can basically create some nonlinear data with any combination of nonlinear functions. So we again have our model here. Let's break the activation functions. Now this looks much better. My model is broken, and the loss also looks broken. So this is one of the first lessons. If you're making your data, make sure that your data is definitely nonlinear. So I think most of you are also thinking this example is way too easy. This is not what I'm dealing with in production. And this was basically only a first primer as an example, because when you're creating actual synthetic data, the data will be heavily dependent on your use case. Now I want to go into a more complex example, which was inspired by my old work. So let's assume we are working for a computer vision company, and we want to identify changes in harbor activity. And we all know managers are very, very eager, so they have set up a big project, very ambitious. We want to monitor harbor activity over a very long time period, let's say 300 time steps, based on satellite data. So you can already imagine it will be quite hard to find a data set like this on some repository that is perfectly labeled and also cheap. So of course, the first issue is that there are way too many time steps. The second issue is that if we would actually buy and label this data, this would be extremely expensive. But when we're at the company, usually we will obtain this data at some point, but we might already want to start training our model and make sure that it's bug-free. So how could we create data for this case? I want you to think of the question again, how would a minimalist artist create or recreate this data? And actually, I think most of you have already done this in a game called Battleship or Schiffe versenken in German, where basically we just have a little square and draw rectangles as our ship. So here is my little ship builder that I would use to debug my model and already train it. And basically, I think this is a really nice example because we can generate our whole training set for debugging with just 2 functions. Basically, what I'm doing here is I have my ocean, and then I have a little square, which is my ship. And with my functions, I can basically generate arbitrary many training examples with different numbers of ships, different ship dimensions, and this only in just 2 functions. So I have my one function, which generates my rectangles or my ships. Basically, it just samples coordinates of ships. And then my second function basically just only iterates over my number of ships and then returns my image. So even though this dataset does not look like a real satellite image, it's still very, very useful for debugging my model because it contains all the basic information that I would need for my actual model. And the other advantage is I can basically generate any label that I would also have in a real use case from these functions because since I generate the ships myself, I already have the positions of the ships. Of course, I think most of you will work in very different fields, so I just want to introduce some other packages for creating synthetic data. Of course, you don't always have to do it by hand. I think especially in computer vision, it's quite handy to do it by hand because it's very intuitive. But yeah, for other applications, for example, there's the time series generator in Python, with which you can generate time series. There's also a package called PlatePy, which I think is very interesting, especially if you want to fill up some databases. So basically here you just have to create a YAML template with different variables. So for example, we're generating a person here, which has the variables age and gender, and I can specify some distributions or some maximum and minimum values. In computer vision, if what I've shown you is too simple for you, there are also some more complicated or more advanced packages like Zumolab ZPy, where you can basically create the objects you're interested in Blender, which is a 3D rendering software, and then automatically obtain labels. Or if you have already created semantic masks, like we did in the ship builder, you can also use GANs or diffusion models to basically generate synthetic images from your segmentation masks alone. So let's have a little check-up on our debugging status. We have talked now about the data components, how to create synthetic data in a very simplistic way to make sure that our data component is definitely isolated. Next, we're going to go to the model components. And I had already mentioned that I want to introduce the concept of pre-train checks here. But I know that maybe some of you have quite a negative attitude about tests in machine learning. And this is usually because we tend to use software engineering testing workflows for machine learning development. But this is actually not a good idea, and I want to go a bit into detail on why this is the case. So here on the left-hand side, you can see what is going on in the typical software engineering workflow. Basically, our customer or our manager is wishing for a feature. We develop the feature. The unit tests pass, and our project is basically finished. So if we would like to apply the same framework to machine learning engineering, we would train our model, then we would have some predefined metric, like 90% accuracy that we want to reach on some test set, and then our project is finished. I think if you're working in machine learning, you already see several issues with this. So first of all, this kind of pre-assumes that we know which model to train, which is not always the case. Second, it kind of presumes that we know what kind of accuracy is reachable on our data, but usually our real-world data is very, very messy. And also, some clever machine learning engineers will definitely find some workarounds on how to reach this 90% accuracy without actually creating a model that's useful. So what can we do instead to make tests and checks useful for our models? Let's look at the machine learning development cycle. So usually how our development cycle looks like is we have an idea, we experiment, and based on the outcome of the experiment, we either have to start our cycle again, or if we are succeeding, we write our unit tests and then deploy our model. But we are basically going to be in this loop usually a couple of times. And most of the time is going to spend in the experiment stage. So this is where we need the most support. And a very useful way to use tests and checks here is that we have something like a machine learning test suite, which basically offers assistance during the experiment phase and also helps us speed up our experiments by preventing the most common bugs. So let's look at an example of a machine learning test suite. I want to show you this package called Torch Test. And it's basically a single function call which you can run before your model. So these pre-trained checks that are offered in this package, for example, test for output ranges, invalid values, and also how the variables or parameters in your model are updated. There's also another version of this called the Torch Check package, which is also quite useful. You can check it out. And I have a little example prepared here with this function assert vars change. There are many more functions here. And here our model is set up. So we have very simple inputs and very simple targets and just build one batch with our data. And then we have our most simplistic model here, which is not even a model, just one linear layer. And how do we use this function? Basically, we call the function, input our model, our loss function, our optimizer, our batch, and our device. And what will happen in this function is if the weights are not updated properly, so for example, if you had accidentally frozen your weights or biases, this function will fail and your training will not even start. So this is a really nice component that you can just put in front of training your model to make sure nothing is going wrong and you're not finding it out after spending a lot of money on AWS. There are also some functionalities to check the output ranges. For example, if you have a sigmoid in your last layer and want to make sure, okay, I'm really getting the output from my sigmoid and not accidentally from some other layer before. And for this, you can basically set up a test suite and then specify the output ranges and also define that you want to test your output ranges. So these are just some examples, but what would the ingredients for a successful ML test suite in general be? If we look at the data loaders, we want to test for data leakage to make sure that nothing from our training set is spilling over to the validation set. We also want to test for in-batch variance to prevent that we're accidentally always returning the same training example if we have some subsetting happening in our data loader. We also want to check for data ranges and invalid values. And of course, we also want to check for the data format, that it has the appropriate input or output shape. The same way for our models, we want to check for weight updates, output ranges, output formats. And usually what is also a bit more complicated to construct, but very, very helpful, is that our model should be able to overfit on a trivial case like a single training example. Another very important ingredient of the machine learning test suite is that usually you don't want to place your tests in the same repository as your project. So from software engineering-based testing, we usually have this setup where I have my package and I have some script called train model here, for example. And then I would set up a tests folder where I have a testing script for each script that is present in my actual package. This is not really helpful for machine learning because you will basically end up writing the same tests over and over again. And this is just a little bit of a waste of time. Also, it kind of brings the danger that you're over-engineering your tests to the model that you're currently trying out. And this is not really what we want from our machine learning tests. A general rule is that if you can't transfer your tests from project to project, you have not written a helpful test for your machine learning test suite. Instead, we would like to have a project-independent test suite, which could look like this. So we have our tests here, and then we have our tests or checks for different components. For example, the data loader, the weights, or also expectation tests. For example, if I assume my model to be invariant to certain input changes. And then when we have built this test suite, we want to import it to any specific machine learning project. So let's have a little recap on what we talked about. So we figured out the data components, so our data should be definitely fixed now. We figured out the model components, so we should be able to catch approximately 80% or 70% of our bugs. I don't want to overdo it now. But still, because machine learning engineers, they're very, very creative, I'm pretty sure we managed to introduce some other bugs to our model as well. So I want to go a bit into post-train tests, which kind of look at how the data and our model interact together. So I want to start off with the post-train test in this package called Weight Watcher. So Weight Watcher basically is a package which gives you metrics for your neural network without having to have access to your training or validation data. So even if you have made some grave mistakes in your data loader that you couldn't identify, or your data wasn't even containing the information to learn a good model in the first place, you will probably see this with Weight Watcher. So I want to show you one very specific metric that this package provides. It's called the alpha value. And this value is computed for each layer in our model. Basically, what the meaning of the alpha value is that we compute the weight correlation matrix, which is basically just the matrix product between our weight matrices for each layer. And if we plot the eigenvalues of this matrix on a histogram, we want the tail of the histogram to adhere to a power law. And this power law should have exponent 2. So this is quite complex, but the only thing you have to remember is, okay, I want my alpha to be at 2, and if I see it at any other values, especially values above 5, this indicates that my trainer is not well trained. And you can find some more theory in this paper linked here. So let's look at our alpha value and how it looks like for our different breakages. So on the right-hand side, you can see the alpha values from my unbroken model, and according to our theory, these values are quite good, so they are around 2. And on the y-axis, you can see the count, so this means I have one layer with alpha value, let's say 1.8 or so. Now, let's break our model a little bit. First of all, let's break the activations. And here I can already see my alpha values are definitely higher than with the model that's working properly. Now, let's break the data loader. Here I'm now seeing some serious issues. One alpha value is very, very close to 4 already, which, like, our alarms should be going off a little bit. Now I freeze the weights. This is a bit counterintuitive, but I think it's from the fact that if I freeze the weights, they're basically stuck at their random initialization. Our model almost looks better than the unbroken model. And now let's freeze our bias. And here again, we see that our unbroken model is a little bit better than our broken model. So this is a metric that is quite helpful for comparing models. Of course, it's not able to tell you everything or also point to exactly what is going wrong, but it can be quite helpful if you really don't have any access to training data or validation data, or if you have serious trust issues to your data because maybe you don't trust your labelers. Another post-train check I want to show you is from a package called CleanLab. Here we basically want to find out whether any examples that we have in our data are mislabeled when we have already trained the model. So we don't want to go through our training examples step by step, but we want to see this in an automated way. This package also has a lot more functionalities, for example, to inspect consensus if you have multiple data annotators, and also provide scores if you don't want to label all your data, but you want to have some active learning mechanism to label your data. And of course also to detect outlier and out-of-distribution examples if you have the suspicion that these are present in your data. And if these are present in your data and you want to get rid of them. So for mislabel classification, we're using a concept called self-probability. The main intuition here is that we're just looking at the class scores that our classifier is producing, which I think is pretty straightforward. And the nice thing about this package is that you can basically input any trained PyTorch model into this package. You just have to make sure that you transform your PyTorch model to an sklearn object. Afterwards, I just have to run this function where I input my model, my training data consisting of the data and the labels, and then here I say, okay, I want to have the predicted probabilities to guide the suggestions of which of my data examples are mislabeled. And then afterwards, I can have a ranked list of indices in my data set that are probably mislabeled. So this sounds very nice, but maybe let's see how it works in action. So I have my beautiful concentric circles here again, and on the right-hand side, you can see my loss curves for a simple classification model. And now let's mix up some labels. So now you can see there are evidently some blue dots in the inner circle, which should be red, so this is definitely not correct. And on the outer circle, I have some red dots, which also should not appear there. But at the same time, in my loss plots, I'm seeing, okay, if I mixed up my labels, my performance is a bit worse, but it's not really something where I would say, okay, I really need to go into my data and look at it again. Now let's run CleanLab. And actually, I think this is really, really nice. Of course, this is a simple case, but CleanLab almost identified all the data points that I have corrupted. So when there's a green circle around the data point, this means that CleanLab would suggest me to look at this example again and potentially relabel it. I think only 2 examples have not been identified. So there's a little red dot lost here, not identified, and a small blue dot here somewhere, which also shouldn't be there. Now, let's wrap up everything. How would I set up a robust model training pipeline so that I'm reducing the potential for bugs as strongly as possible? First, if I'm not 100% sure that my data is perfect, so unless you're training on MNIST or something similar, you should consider creating some simplistic synthetic data and keep this rule in mind. Okay, how would a minimalist artist create my data? Before I give my synthetic training data to my model, I want to run pre-train tests or pre-train checks on my model to make sure that the behavior of my model is as expected. When I have a successful training run with my synthetic data, so all the metrics are looking fine, I can actually start training on the real-world data. And if I have done that, and then I want to check my training and validation metrics as always, but I think it's also very useful to have some post-train checks, for example, to check if you can improve your data again. And if everything is going well, of course, this is our dream, we can finally add our model to our model zoo. So let's wrap up what we have been talking about today. So I know we talked about debugging on a very, very high level and not go into the intricate details because this can just be like a little bit overwhelming if I just present a list to you like, oh, this can go wrong, this can go wrong, this can go wrong. Usually the issue we have is that we know something is wrong, but we don't quite know where to look. And if we have these three components, they will guide us a little bit into which components we should have a deeper look to see if something is going wrong here. So the first component was synthetic data creation. And what I really want you to take from here is that your synthetic data does not have to look like your real data. It can be super, super simple. You really just want to use it for debugging and not for generalization. The second thing I want you to remember is pre-trained tests, they don't have to be complicated. And you should also only write them once. You don't have to write them for each project. They can be as easy as one function call. So for example here, I have my model. I test the model. Everything fine. I have my data loader, I test my data loader, and then when I start my training, I should be able to already rule out a plethora of bugs that would be very hard for me to identify otherwise. The third thing I want you to remember is post-train checks exist, and they can be very, very helpful, especially if you didn't catch some bugs that happened before in your pipeline. And usually these metrics from post-train checks are also quite robust to any data issues or can even help you identify data issues. So I hope this talk was useful for you. And of course, I'd be super, super happy if I hear at least one story of a bug that was caught with one of these methods. After the talk, also feel free to come talk to me if you have anything to share or any other recommendations. If this was too high level for you, I also have on my GitHub some more recommendations for more in-depth reading. For example, some resources from Andrew Karpathy, how to tune your hyperparameters, and also some more in-depth views on how to create tests and checks for your test suites. Yeah, so then I would say let's call it a wrap, and I'd be happy to take some questions from you.
Yes, so thank you very much for the deep insights and the really helpful cookbook. We have some questions in Slido, so I'll go through them from bottom to top, but I think some you have already answered. So the first one is, what library did you use to create your amazing slides?
Thank you. Oh, actually, I think you should. I'm sorry. Yeah, it's Streamlit. So I was not scrolling down. Yeah, it's Streamlit. It's very easy to use, so I can really recommend it. Yeah.
Okay. So the second one is, are there options to check for non-obvious data leakage, like different images from the same subject that should not be split into train and test?
Probably they are. I would say you have to use some metadata if you have that available. Otherwise, maybe some similarity scores. But I haven't, like when I was researching about this topic, I haven't come across anything here. So maybe it would be a good opportunity to build something as well.
Are there any packages or libraries that create synthetic data with noise, like outliers, error points, and such, not just perfect distributed data?
I'm pretty sure they are. I think there are also several talks coming up about synthetic data in the course of this conference. Usually what I see when you're creating synthetic data, not for debugging, that you can input different parameters. So I would probably just play around with the parameters of your synthetic data creator. For example, if you have a gun or variational autoencoder, just introduce a distribution shift there.
Okay. How about debugging issues at training the model in a different environment, local versus cloud, or CPU versus GPU?
That's a very good question. Probably you should make sure that you have a transferable environment like Poetry, Anaconda environment. Then I couldn't imagine that so many issues are occurring, but in general, I would recommend that you make sure that your model is bug-free before scaling it somewhere.
Okay. Which problem would you recommend to start with? Meaning that there might be more than one problem bug in your code. Where is it better to start?
I usually like to start with my data because I work in computer vision and I like looking at images. And I would say 50% of the time something is wrong with my data. So usually what I do is I just take a single example and overfit on that. And if this is already not working, I know something is in my model structure. But if this is working fine, I know, okay, I have to look at my data because something is going wrong there.
There's a question on which model was used to predict probabilities for the clean lab case, corrupt or original?
Yeah.
You can go back.
Oh, I think the same model as before. I think it had 5 or 8 layers, so just a densely connected network. It's also in the repository under the Torch examples if you want to have a look.
Okay. Does it imply that packages should appear soon that provide such generic test suites? Maybe you can create one yourself.
Yeah, this is a very interesting question because from my experience, I really like the setup with pre-train tests and post-train checks. And there are also some packages, but they don't seem to be in usage so much. So I'm kind of like interested if there will be a paradigm shift of people like really pushing to use these packages and create these packages, or if developers just enjoy debugging by hand, because I mean it's also something you can be very proud of if you find your bug without any help. Yeah.
Do you have any preference for test frameworks, e.g. PyTest?
In general, yes, PyTest, but I would say for a machine learning test suite, you don't really need a specific testing framework, as you're basically just building one repository where you just have these functions like test model or test loader, which basically just contain assert statements. And here I think it's also quite handy to run them before the training and not have like a separate test run, for example, before you're pushing somewhere. Because then if you're still experimenting, you really catch your bugs right before you perform your training.
Okay. Last question. Is Weight Watcher only working well when you already have a pretty well working model in your experience?
No, I would say that the main goal of Weight Watcher is that that you can put any model into it. But in my experience, it works quite well for model comparison. Especially, for example, if you want to compare pre-trained models to see which one is more suitable for your data. And also if you do model compression to check that nothing has broken during your model compression. For example, you've compressed too much, but in general, you can put any model into this. But I also don't have like a clear recommendation of which metric is the best, so I would recommend to look at all metrics as a whole.
Okay. Time is up, but I'm sure you can come and approach Clara and ask your questions in case you still have any. And thank you again for a very fantastic talk.